All right, today we're going to learn how to set up a mass spring system. Now I'm going to link some other videos down in the description to help you with this mass spring system. So one of the videos is how do we deal with energy with a mass spring system. One of them is an example. One of them is how do I know that this is what I need to do when I'm doing simple harmonic motion. And then another one is how do I deal with graphs of simple harmonic motion. Another example with a mass spring system. So let's get started on how we set up a mass spring system problem. So the first thing we need to understand is that for a spring, we're going to use Hooke's law. This is important because our force is proportional to the opposite of the displacement. This means we're going to have simple harmonic motion. And our goal when we get simple harmonic motion for this setup is we want to get an equation that's in the form of A is equal to negative omega squared x. And we want to figure out what is the omega for this type of simple harmonic motion. Again, the reason we want to do this is linked in the general simple harmonic motion setup video below. So this is where we're going to start. This is the force from the spring. Now I have my spring oscillating on a horizontal frictionless surface. And so when I sum up the forces acting on it, it's going to be MA. I have this force, my negative kx, is the only force acting on it. Now this is a vector equation. This just means that the acceleration is going to be in the opposite direction of the displacement. So if it's displaced this way, the spring is trying to accelerate it back that way. All right. Now my next goal is I want to get it in this format. So I'm going to move the m over, so I'm left with acceleration is equal to negative k over m times x. And so I have this format, a equals negative something times x, and that something is k over m, and so I know that omega squared is k over m. And so now I can figure out what omega is. And omega is the angular frequency of this simple harmonic motion, and it's equal to the square root of k over m. From there I can create a period equation. And I know that the period is equal to 2 pi divided by that angular frequency. And so my period is equal to 2 pi times the square root of the inverse of this, so m over k. Now, we are going to look at a couple things. What happens if I change the mass, the spring constant, and the displacement? What happens to our situation? So if I change the mass, okay, so if I change the mass, if I give it more mass, okay, so I make this mass term bigger on the bottom, which is an inverse relationship to my acceleration gets smaller. So I have a smaller acceleration value. Okay? Smaller acceleration value leads to a smaller velocity, which leads to a smaller period, you would think. It would take longer. And yes, we see that if the mass increases, the period increases. I don't know if I said that right there before. So the mass increases, the period increases. It takes longer, so the period increases. All right, let's change the spring constant, how stiff and how much force that spring can apply. So if I increase the spring constant, that's going to increase my acceleration. They are directly related. Okay, so that means my acceleration is going to go up. That means my velocity is going to go up. And if my velocity goes up, it would wager that it's going to take less time to complete one oscillation, and so my period should go down. And so I see that if I increase k, that decreases my period. Okay. Now, what happens if I change my displacement? Okay, so what if I pull it back further? Okay, so if I increase my x, okay, my acceleration increases. If I pull it back further, it's going to be moving faster too, yeah. So my velocity goes up as well, because not only do I have a larger acceleration, I have a longer distance over which to accelerate as I get back to that middle point, but you might say, okay, I've increased the acceleration, I've increased the velocity, but I haven't changed the mass, I haven't changed the k, so my period doesn't change. So how can that be? How can I have increased the acceleration, increase the velocity, oops, but the stays the same. How do I get the period to stay the same? Well, this is what you need to think about. All we've done is change the amplitude. So now, yes, it has a bigger acceleration. Yes, it has a larger velocity, but it has a longer distance to go. So because it's going a longer distance, it turns out it takes the same amount of time to do that. Okay. But it does change the energy, and so that's what we're going to look at in that other video that's linked down below about how does energy affect a system with a mass and a spring. There you go.